Lesson 29, Nuclear Fusion and Fission. Fission. Fission sounds like fissure because that's what it's about. It's about breaking an atom into two pieces. Nuclear fission occurs when a larger nucleus splits apart into two smaller nuclei. Here's an example of nuclear fission. A uranium nucleus breaks apart into krypton and barium. Fusion. Nuclear fusion occurs when two smaller nuclei combine together to become a single, larger nucleus. It happens primarily in stars. For example, helium is produced with the fusion of deuterium and tritium, both isotopes of hydrogen. Part 1. The fission of uranium. Uranium-235 is a common fuel used for fission to produce nuclear energy. The process goes like this. In the first step, you hit a uranium-235 nucleus with a fast-moving, high-energy neutron. They combine for a moment, and the atom becomes a uranium-236 atom. Uranium-236 is too unstable to stay together very long, and the atom breaks apart into two smaller nuclei and a couple neutrons. Some of the mass of the original uranium-235 and neutron is converted into energy. There's a couple possible equations that could describe the fission of uranium-235. In the first one, we have uranium-235 with atomic number 92, and we hit it with a single neutron. This produces, for a moment, uranium-236. But uranium-236 is not stable enough to last very long. It breaks apart into barium-141 with atomic number 56 and krypton-92 with atomic number 36. And 3 single neutrons are also released in the process. There's a second possible equation. We start again with uranium-235 with atomic number 92 and bombard it with a single neutron. For a moment, uranium-236 forms, but that's only for a moment. The uranium-236 breaks apart into xenon-140 with atomic number 54 and strontium-94 with atomic number 38, and 2 neutrons are released. Either situation is possible in the fission of uranium. Chain reactions. The fission in a nuclear reactor is self-sustaining. The original fission reaction, for when uranium produces krypton and barium, produces 2 neutrons. Those 2 neutrons are released and collide with 2 new uranium atoms. These collisions produce 2 neutrons each to make a total of 4, so now we have twice as many neutrons as before. These 4 neutrons can now collide with 4 uranium atoms, producing 8 more neutrons to collide with other uranium atoms. This is called a chain reaction, and if it is not controlled, the sample of uranium can explode with huge amounts of energy. If the neutrons are shielded and reflected back into the uranium for long enough, about 1 millisecond, the reaction results in an atomic explosion. However, a controlling device can be used to control and reduce the rate of the reaction. A stable, controlled reaction produces heat that can be used to heat water into steam and then drive a steam turbine to create electricity. Can-do reactors are the type of reactor we use in Canada. They use heavy water to slow down the chain reaction site and control the overall reaction. In Canada, we have many different ways of producing electricity. In Alberta, the bulk of the energy is produced using coal power. Coal is a non-renewable energy source that produces a great deal of greenhouse gases. Hydroelectricity is renewable, and it's clean. It doesn't produce any greenhouse gases. Nuclear energy isn't entirely renewable because it requires a supply of uranium as a fuel source, but it is very clean, a very efficient source of fuel, and it doesn't produce any greenhouse gases. Most nuclear power is used in Ontario, with a little bit in Quebec and New Brunswick. But all of Canada's nuclear power is out in eastern Canada. Example, calculate the energy released in one fission of uranium-235 into krypton-92 and barium-141. The equation for this nuclear reaction is uranium-235, 92, plus 1 neutron turns into krypton-92 with atomic number 36 plus barium-141 with atomic number 56. In the reaction, 3 neutrons are also produced. We'll start by calculating the initial mass. The initial mass is the mass of uranium plus the mass of the neutron. This is 235.0439299 atomic mass units plus the mass of the neutron, which is 1.008664916 atomic mass units. This gives us an initial mass equal to 236.052394816 atomic mass units. We can also calculate the final mass. The final mass will be the mass of krypton plus the mass of barium plus 3 times the mass of a neutron. So the final mass is equal to 91.92615621, the mass of krypton, plus the mass of barium, which is 140.91441109, plus 3 times the mass of a neutron, which is 1.008664916. This gives us a final mass equal to 235.866501967 atomic mass units. The change in mass is the final mass minus the initial mass. This is negative 0.185832849 atomic mass units. We convert this into kilograms by multiplying by 1.66 times 10 to the minus 27 kilograms per atomic mass units, which gives us a change in mass equal to 3.0858269 times 10 to the minus 28 kilograms, and this is negative because this mass has been lost. Using this change in mass, we can determine the amount of energy released. E equals mc squared. So the energy released is the mass, 3.0858269 times 10 to the negative 28 kilograms, times c, which is 3 times 10 to the 8, squared. This gives us an energy in joules equal to 2.7772441 times 10 to the negative 11 joules. We divide this by 1.6 times 10 to the negative 19 joules per electron volt to convert it into electron volts. And this gives us an energy equal to 173577756 electron volts. If we divide this again by 1 times 10 to the 6 electron volts in a mega electron volt, it gives us an energy equal to 174 mega electron volts. So in the fission of uranium-235 into krypton and barium, we release 174 mega electron volts for each fission reaction. Part 2, fusion of hydrogen. In nuclear fusion, we take light elements and force them together to form larger-sized atoms. Nuclear fusion reactions require extremely high pressures and temperatures to get them started. Such pressures and temperatures are found within the core of a star, like our Sun. In a star, the nuclei are forced together due to the enormous gravitational forces involved. In turn, the forces created by the fusion reactions try to explode the star. Thus, there is a balance between the forces of gravity and the forces produced by the fusion reactions. Here are the equations for hydrogen fusion in the Sun. We have hydrogen plus hydrogen, which is hydrogen 1, 1 plus hydrogen 1, 1, yields deuterium. Deuterium is an isotope of hydrogen with 1 neutron and 1 proton. It's H2, 1, plus a positron, which is E0 plus 1, and a neutrino. The next equation is when deuterium, produced by the hydrogen plus hydrogen, collides with another hydrogen atom. This is H21 plus H11, and this yields helium-3, which is He3, 2 protons and 1 neutron, plus energy, often released in the form of gamma radiation. In the Sun, we also have helium-3 colliding with helium-3. This is helium-3, 2 plus helium-3, 2 yields helium-4, 2, which is an alpha particle, plus single hydrogen 1, hydrogen 1. These two hydrogens are now available to collide with each other to form deuterium, and the process can start again. Here is a fusion example. Calculate the energy released as hydrogen fuses with deuterium, which is hydrogen 2, to produce helium-3. The nuclear equation looks like this. We have hydrogen 1 plus deuterium, which is hydrogen 2 fusing to produce helium-3, which is helium-3 2. The initial mass initial, is the mass of the hydrogen plus the mass of the deuterium, which is 1.007825037 plus 2.014101777785 atomic mass units. This gives us an initial mass equal to 3.0219270985 atomic mass units. The final mass is just the mass of the helium. This is 3.01602931914 atomic mass units. The change in mass is the final mass minus the initial mass. The change in mass in atomic mass units is 0.00589777941 atomic mass units. We can convert this into kilograms, and we get a change in mass in kilograms equal to 9.79349226 times 10 to the negative 30 kilograms. These are both negative because mass has been lost. We can now calculate the amount of energy released. E equals mc squared. So we multiply the mass that's been released, which is 9.79349226 times 10 to the minus 30 kilograms, times c squared, which is 3 times 10 to the 8 squared. This is an energy released equal to 8.814143 times 10 to the negative 13 joules. When we convert this into electron volts, we get an energy equal to 5508839 electron volts, which is 5.5 mega electron volts released for every fusion of hydrogen with deuterium. Element formation in stars. 75% of the matter in the universe is in the form of hydrogen, or single protons. In fact, it's from hydrogen that all the elements are eventually synthesized. This process occurs through a series of fusion reactions within stars. Our Sun is an average star that is currently halfway through its life cycle. The main reaction that powers the Sun's energy is a series of reactions leading to the formation of helium from hydrogen. Some of the elements larger than helium can be produced by fusion in stars larger than our Sun. Other elements can only be produced in huge energetic events like supernovae. So the story of element formation goes like this. 13.7 billion years ago, there was a great big explosion called the Big Bang. 370,000 years later, hydrogen atoms and molecules started to appear. 100 million years later, the stars started to appear and fusion began. In blue and yellow stars, hydrogen was converted into helium. In red and red giant stars, as well as blue-white stars, conversion from helium to carbon to nitrogen and oxygen occurred. In blue-white stars, we got sodium, magnesium, aluminum, silicon, phosphorus, sulfur, chlorine, potassium, calcium, magnesium, and iron. And as the stars started to go supernova, that's when we started to see some of the other larger elements: nickel, copper, zinc, silver, gold, mercury, and lead, for example. To quote Carl Sagan, "The nitrogen in our DNA, the calcium in our teeth, the iron in our blood, the carbon in our apple pies were made in the interiors of collapsing stars. We are made of star stuff." So here is an old picture of me, or you, which you could post as next week's Throwback Thursday selfie.
The cosmos is also within us. We're made of star stuff. We are a way for the cosmos to know itself.